James Webb just found something inside an interstellar comet that should not be there. Not in those quantities, not at those ratios, not according to anything we knew about how comets form, how planetary systems work, or how the chemistry of the galaxy is distributed across billions of years of cosmic time and across the vast distances between the stars. The numbers that came back from Webb's instruments are so far outside anything previously recorded in any comet from any source, anywhere in the solar system or beyond, that the researchers who spent months analyzing the data used the word surprised. Scientists do not use that word lightly. And what surprised them changes our understanding of this visitor from another star in ways that are only beginning to be fully absorbed by the scientific community. On June 22, 2026, a paper published in the journal Nature by researchers using the James Webb Space Telescope revealed two findings about the interstellar comet 3I Atlas that nobody in the field had predicted, and that the researchers themselves described as surprising. The first was that the comet's deuterium levels are approximately 30 times higher than anything ever measured in a comet from our own solar system. 30 times, not 30% higher, 30 times higher than the maximum ever recorded anywhere in the solar catalog. The second was that the chemical ratios of carbon and deuterium in the comet's coma are unlike those found in any solar system object ever studied, pointing to a formation environment so cold, so ancient, and so fundamentally different from the conditions that produced our own solar system's comets that the word alien has never been more scientifically precise. This is the full story of what James Webb actually found, why it is so extraordinary, and what it means for everything we thought we understood about the universe beyond our own cosmic neighborhood. Start with what deuterium actually is. Deuterium is a form of hydrogen, the most abundant element in the universe, but with a difference. Normal hydrogen has a nucleus consisting of just a single proton. Deuterium has a nucleus containing one proton and one neutron, which makes it heavier than ordinary hydrogen. This heavy hydrogen, as it is sometimes called, was produced in the first few minutes after the Big Bang, alongside ordinary hydrogen and helium. The ratio of deuterium to ordinary hydrogen in any given object is one of the most sensitive tracers of the conditions in which that object formed. The reason is thermodynamics. In extremely cold environments, chemical reactions preferentially incorporate deuterium into molecular compounds at a higher rate than in warmer environments. The colder the environment where a molecule forms, the higher its deuterium content will be relative to its ordinary hydrogen content. This effect is called deuterium fractionation, and it is one of the primary tools that astronomers use to trace the thermal history of molecules in space. Comets from our own solar system have deuterium to hydrogen ratios that have been measured carefully across dozens of objects over decades of observations. Those ratios are relatively consistent with each other and consistent with the conditions that existed in the outer solar system, specifically the cold outer disk that surrounded the young sun as the planets were forming, where temperatures were well below minus 200 degrees Celsius, and where deuterium fractionation was significant, but bounded within a range that reflects the thermal history of our own solar neighborhood. The highest deuterium enrichments found in solar system comets are elevated compared to the bulk deuterium content of the interstellar medium, reflecting the cold chemistry of the outer solar disk. But they have a ceiling set by the physical conditions that existed in our solar system's formation region more than 4.5 billion years ago. Webb's NIRSpec instrument revealed exceptionally high levels of deuterium in 3I Atlas, about 30 times more than seen in solar system comets, 30 times beyond that ceiling. This is not a modest elevation. This is a measurement that sits in a completely different part of the parameter space from anything in the solar system catalog. To produce deuterium enrichment at that level requires formation in a thermal environment far colder than anything in our solar system's formation region, conditions achievable only in the deep outer regions of an exceptionally cold planetary system or in a dense molecular cloud, the kind of cold, dark nebula from which star systems form, but one with conditions significantly more extreme than those of the solar nebula that produced our sun and planets. The deuterium ratio in 3I Atlas is not just different from solar system comets, it is so different that it implies a formation history that our solar system simply did not produce. The carbon isotope ratios that Webb measured tell a complementary story. Webb captured detailed data, including chemical ratios of carbon and deuterium that are not found in solar system comets. Carbon exists in two stable isotopic forms. Carbon-12 is the most abundant, making up roughly 99% of all carbon in the universe. Carbon-13 is heavier, containing an extra neutron, and makes up roughly 1%. The ratio of carbon-12 to carbon-13 in any object is, like the deuterium ratio, a tracer of the conditions in which the carbon-bearing molecules were formed and processed. Organic molecules formed in cold, dense interstellar environments have characteristic carbon isotope ratios that differ from those of molecules formed in warmer conditions. The carbon ratios in 3I Atlas's coma do not match those of solar system comets. They match the signature of a formation environment that was colder, denser, and chemically more primitive than the environment that produced the ices in our own comets. Working backward, astronomers use the components that make up Comet 3I Atlas to understand the environment in which it formed, and one revelation is that 3I Atlas appears to be 10 to 12 billion years old, nearly 3 times the age of our solar system. The age determination comes from the combination of the isotopic ratios and modeling of the stellar and chemical evolution of the Milky Way. Stars formed in the early galaxy had different initial chemical compositions than stars forming today, because the abundance of heavy elements in the galaxy has been building up over time through successive generations of stellar nucleosynthesis. A comet with isotopic ratios pointing to formation in conditions characteristic of the early galaxy, combined with the methane and carbon dioxide abundances detected in the earlier campaign, provides converging lines of evidence pointing to an age well beyond the 4.6 billion year history of our own solar system. If that age estimate is correct, 3I Atlas formed when our sun did not yet exist. It has been drifting through the galaxy for longer than Earth has been a planet. It crossed into our solar system during a human lifetime, and we happen to have the right instrument in orbit to measure what it carried. To understand why the deuterium finding is described as impossible in the context of how scientists talk about things that exceed their models, you need to understand what the word impossible means in this context. It does not mean physically impossible in the sense of violating the laws of physics. Deuterium fractionation at this level is physically possible under the right conditions. What is impossible is producing a deuterium enrichment 30 times beyond solar system levels within any model of how comets form. In a planetary system similar to ours, under the timescales and thermal conditions that our models of planetary system formation describe. If 3I Atlas formed in a planetary system around a star, that star's protoplanetary disk must have had conditions dramatically more extreme than the conditions models predict for any star currently in our galactic neighborhood. Either the star that formed 3I Atlas was in a profoundly different environment, possibly in the dense inner regions of a much younger Milky Way where molecular cloud conditions were more extreme, or the comet spent an extended period embedded in an exceptionally cold interstellar environment after its ejection from its home system, which would have allowed further deuterium fractionation to continue accumulating in its outer ice layers. Both possibilities are scientifically fascinating, and neither is yet definitively established as the explanation. Martin Cordner of the Catholic University of America and NASA's Goddard Space Flight Center led the NIRSpec observing campaign that produced the Nature paper. He received what NASA described as director's discretionary time, an interruption to Webb's carefully planned observation schedule, to point the telescope at 3I Atlas as the comet was retreating outward from the Sun in the weeks following its perihelion passage. These directors' discretionary time observations represent some of the most valued and most competitive telescope time in all of modern astronomy, reserved specifically for targets of exceptional and unanticipated scientific significance that were not known when the original observing schedule was built. The fact that the Webb Director's Office approved the interruption of already scheduled science programs to study 3I Atlas reflects the unanimous consensus within the astronomical community that this object, this 10 billion-year-old visitor from the early galaxy, represented a genuinely once-in-a-lifetime observational opportunity that could not be allowed to pass without the most capable instrument in orbit being pointed at it. The observation window that made the June 22nd paper possible was exceptionally narrow. Comets are most chemically productive near perihelion, when the heat of the sun vaporizes their ices most actively. As they recede from the sun, their activity drops rapidly. The December 2025 observations, taken when 3I Atlas was between 329 million and 379 million kilometers from the Sun, roughly 2.2 to 2.5 astronomical units, captured the comet in a state where its nucleus was still actively releasing gases warmed by the recent solar encounter but had not yet frozen back into dormancy. That window, a matter of weeks, was the best opportunity Webb would ever have to read the isotopic composition of 3I Atlas's inner ices, the ancient material that had been sealed inside the nucleus since its formation in the early galaxy, and was now being exposed to sunlight for the first and only time in its existence. As of early 2026, 3I Atlas was already past Jupiter's orbit and observable only with great difficulty. It will not return. The broader context of the June 22nd Nature paper is what makes it feel like the beginning of a new chapter in science, rather than the conclusion of one. ESA confirmed in its own coverage that the deuterium and carbon isotope data from Webb represent the first time isotopic evidence has been used to trace the origin of an interstellar object, establishing a new methodology for understanding where future interstellar visitors come from. The The paper states explicitly that analysis of these interstellar objects is a major step toward learning how common or uncommon the conditions for the evolution of life are in the universe. The connection between the comet's deuterium ratio and the question of life's cosmic prevalence is not incidental. Deuterium-rich environments are also environments where the organic chemistry that preceded life on Earth was likely occurring in forms and at scales we have not yet directly observed. The discovery of the impossibly high deuterium ratio in 3I Atlas also forces a reconsideration of assumptions in the study of the other two confirmed interstellar objects. Oumuamua, discovered in 2017, was too far from the Sun by the time it was detected to allow the kind of detailed spectroscopic analysis that Webb performed on 3I Atlas. No gas coma was detected around Oumuamua. No isotopic data was collected. What little was measured about it pointed to unusual properties, including a non-gravitational acceleration that some researchers attributed to outgassing of hydrogen gas invisible to available instruments, and others found difficult to explain through any single known mechanism. The debate over Oumuamua's nature, whether it was an unusually flat and thin rock tumbling through interstellar space, a hydrogen iceberg, a nitrogen shard from another planetary system, or something more exotic, has never been fully resolved because the observations that would have settled the question were not made in time. If Oumuamua had deuterium enrichment comparable to or exceeding what Webb found in 3I Atlas, the hydrogen outgassing models for its non-gravitational acceleration would need to be revisited with the new isotopic context in mind. A hydrogen-rich, deuterium-enriched composition could change the mass estimates, the outgassing rates, and the overall physical interpretation of Oumuamua in ways that the 2017-era data cannot fully constrain. We simply cannot know. The observational data that would settle the question does not exist. But the 3I Atlas result raises the question in a way it could not have been raised before June 22nd, 2026. 2I Borisov, the 2019 interstellar comet, was more thoroughly characterized than Oumuamua, but was observed at a point in its trajectory, where its activity was lower and the signal quality from available instruments was less than what Webb achieved with 3I Atlas. Deuterium measurements of 2I Borisov were attempted, but did not reach the sensitivity needed to constrain the isotopic ratio at the level achieved in the June 22nd paper. Whether 2I's Borisov carried the same extreme deuterium signature that 3I Atlas has now revealed is an unanswered question that will only be resolved when the next interstellar visitor arrives and is observed early enough for Webb or its successors to apply the same isotopic analysis techniques. The Vera Rubin Observatory, which launched its full legacy survey of space and time on June 30th, 2026, is the most important ground-based instrument in the world for ensuring that the next interstellar comet is detected early enough for a complete observational campaign of this kind. Rubin scans the entire southern sky every few nights with a 3.2 gigapixel camera sensitive enough to detect objects far fainter and far more distant than any previous sky survey. A new interstellar visitor, crossing into the outer solar system, would appear in Rubin's data as an object with an unusually high velocity relative to background stars, a signature detectable automatically by the real, time-alert systems that process the nightly survey data in minutes. If the next interstellar object is detected further from the Sun than 3I Atlas was when first spotted, the entire scientific community would have more time to plan and execute the comprehensive isotopic and chemical characterization campaign that the June 22nd paper demonstrates is now scientifically achievable with Webb. The connection between the extreme deuterium enrichment in 3I Atlas and the question of life's cosmic distribution is not a rhetorical one. It reflects a genuine scientific relationship that astrobiologists have been tracking for decades. The molecules most critical to the origin of life on Earth, amino acids, nucleotides, complex organic compounds, form in the cold, dense regions of molecular clouds through reactions that are strongly influenced by deuterium fractionation chemistry. In environments where deuterium is heavily enriched in molecules, the same low-temperature chemistry that drives that enrichment also drives the formation of complex prebiotic organic compounds at rates that are higher than in warmer environments. The interstellar molecular clouds where stars form are some of the most chemically active environments in the galaxy precisely because they are so cold. Cold enough that exotic chemistry can proceed that would be thermally impossible at higher temperatures. If 3I Atlas formed in an environment with deuterium enrichment 30 times greater than our solar system's formation region, it also formed in an environment with prebiotic chemistry 30 times more active, at least along the deuterium-sensitive pathways that researchers use as proxies for overall cold chemistry productivity. What that means for the organic inventory of 3I Atlas beyond what Webb has already detected is a question that the forthcoming dust composition paper from the MIRI campaign may begin to address. The team noted at the time of the June 22nd paper's release that a separate analysis of 3I Atlas's dust composition using MIRI data was being prepared and would be reported in a forthcoming publication. If that dust analysis reveals organic molecules at abundances or complexities beyond what solar system comets carry, the picture of 3I Atlas as a carrier of prebiotic chemistry from the early galaxy becomes dramatically more specific and more scientifically compelling. The question of whether 3I Atlas's extreme chemistry is unique to it or representative of a broader population of interstellar objects from the early galaxy is one that cannot be answered from a single object. It requires a statistical sample. It requires detecting and characterizing multiple interstellar visitors with the same level of isotopic detail that Webb applied to 3I Atlas in December 2025. IF, the next several interstellar visitors, all show deuterium enrichments comparable to 3I Atlas. It would suggest that old galactic objects are common among interstellar comets, and that the early universe produced comets with dramatically different chemistry than our solar system comets on a regular basis. If subsequent visitors show solar system-like isotopic ratios, it would suggest 3I Atlas is an outlier, a particularly ancient and unusual traveler, rather than a representative sample of the interstellar population. The field of comparative interstellar comet chemistry is now a real discipline, rather than a theoretical aspiration. 3I Atlas's June 22nd paper is its founding document. The Roman Space Telescope, launching August 30th, 2026, adds complementary infrared detection capability that could extend the distance at which interstellar visitors are first identified, potentially giving astronomers months of additional preparation time before the next interstellar comet is anywhere near perihelion. What James Webb found in 3I Atlas is simultaneously a measurement of a single object and a window into the full chemical diversity of the galaxy across its entire 13.6 billion year history. Every comet in our solar system formed in our solar system. The isotopic ratios in our comets reflect the conditions in our solar nebula 4.6 billion years ago. They are all, in a real sense, variations on the same theme, written in the chemistry of the same protoplanetary disk, shaped by the same stellar system, limited to the range of conditions that existed in our one corner of space at one point in time. 3I Atlas, with its deuterium enrichment 30 times beyond anything in that catalog, has demonstrated that the range of conditions across the galaxy, across cosmic time, is dramatically broader than our local sample suggested. There are planetary systems out there, formed in environments so much colder and so much older than our own, that the comets they produce look fundamentally alien by every chemical measure we can apply. And we now have the instruments to read those measurements, we have the methodology, we have the precedent. The question is only whether the next interstellar visitor arrives while Webb is still operational, and whether we detect it early enough to use the full window of its solar approach before it retreats forever into the interstellar dark. And that comet just passed through. It carried its ancient ice here from the early galaxy, warmed it in our sun's light long enough for Webb to read its secrets, and has now retreated back into the darkness from which it came. It will not return for any timescale relevant to human civilization. What it left behind is data published on June 22nd, 2026 in the journal Nature. Data that tells a story about the universe that no instrument built before the James Webb Space Telescope could have read, about a comet that no generation before ours could have detected and characterized in this detail from a place in the galaxy so ancient and so cold that the word impossible as a description of its chemistry turns out to mean exactly what the researchers intended. We found something impossible, and we read every word of it before it disappeared.